Namaste. Welcome to lecture series on Mastering Bioprocess Engineering Numerical Solutions from Pauline M. Doran's Bioprocess Engineering Principles. In the previous videos, we solved some of the problems given at the end of the chapter 2. Let us continue further and solve some more problems. The next 2.11, the problem is mass and weight, the correlation between the mass and weight. And it is asked the density of water is 62.4 lbm per feet cube. What is the weight of 10 feet cube of water? Two cases. In the first case at sea level and 45-degree latitude, and B somewhere above the earth surface where gravitation is G is equal to 9.76 meter per second square. It is very simple problem, but it needs some basic understanding of what is weight and what is mass. We all of us get confused frequently because these terms are used as kind of a synonyms, right? Mass and weight, but there is a technical difference between weight and mass. So let us understand what it is. Problem 2.11. So what is the definition of density? Density, we can define it as density is defined as, that is, rho is equal to mass by volume. So you have a confusion, why do we need density? Because it is asked the weight of 10 feet cube of water. So it's kind of volume is given, so we don't know what is the mass. So to know the mass, we need to know the density of that particular component. So therefore so mass can be written as density. This is the density term into volume, density into volume. So now to calculate as per the data, the problem in that problem statement it is given. So what is the density? That is 62.4 lb mass per feet cube multiplied the volume is 10 feet cube. So feet cube get cancels. So we end up in getting 624 lbm. So now further go ahead and we need to understand what is weight. So from section 2.3, if you read this particular section, you can understand weight is the force with which a body is attracted to the center of the earth by gravity. So as given in the again in the same section 2.3, this force is the mass of the body multiplied by gravitational acceleration. Okay, so and let us see step by step A, sub question A. So if you check the equation 2.18 at sea level and 45-degree latitude. So the G, that is gravitational acceleration, G is nothing but 32.174 feet per second square. So this is the gravitational acceleration. G is nothing but gravitational acceleration. Therefore weight is equal to, that is 624 lb mass. So multiply by gravitational acceleration, that is 32.174 feet per second square. So this becomes 2.008 into 10 raised to 4 lb mass feet per second square. Now let us convert into lb force, because in the particular system we need to convert this into lb force. So converting these units to lb force using using equation 2.19. So, that is 1 lbf is equal to 32.174 lbm feet per second square, Now, let us convert this one. So, that is 2.008 into 10 raised to 4 lbm feet per second square. So, we will convert it, that is nothing but 1 lb force is nothing but 32.174 lb mass feet per second square. So, if you divide this by this particular 2.00 into 10 raised to 4 divided by 32.174, you end up with 624 lb force. So, what is the meaning of this? See, we got 624 lbm, again we got 624 lbf. That is when g is equal to 32.174 feet per second square. So, lb mass is equal to lb force. So, if there is any variation in the gravitational acceleration, obviously this lb mass and lb force will vary, but when this g is 32.174 feet per second square, lb mass is equal to lb force. So, let us move to the next section, that is it is asked somewhere above the earth surface where g is equal to 9.76 meter per second square, little lesser than the regular normal value, that is 9.8. So, it is lesser. Let us see what would be the lb mass and lb force. So, you can go to the table A1, and in appendix A, we know that because given unit is in meter, so we need it to convert into feet. So, that is the reason 1 meter is nothing but 3.281 feet. So, let us calculate same as what we did in A, So, what is that? Weight is equal to that is 624, that is lb mass, the same component lb mass, but here we are going to multiply it by 9.76 meter per second square. We need to add a conversion factor here, that is nothing but 1 feet or 1 meter is nothing but 3.281 feet. Okay, meter get cancels. Now, you end up in 1.998 into 10 raised to 4 lb mass feet per second square. Yes, now let us convert this to lb force. So, how do we convert? We just know we need to multiply by its conversion factor. So, that is weight is equal to 1.998 into 10 raised to 4 lb mass feet per second square. So, we know 1 lb force is nothing but 32.174 lb mass feet per second square. So, this becomes 621 lbf. So, we can understand if the gravitational constant is not equal to 32.281, obviously the weight lbm is not equal to lbf. So, let us move to the next problem. Next 2.12 problem is based on molar unit. So, what it is asked, if a bucket holds 20 lb pounds NaOH, how many, there are 3 sub questions, lb mole of NaOH, gram mole of NaOH, kilogram mole of NaOH does it contain? It is a simple problem. If you know the definition of how do you convert mass to moles and moles to mass, it is an easy problem. So, let us see the solution. Problem 2.12. So, we need to know the molecular weight. It is very important to know the molecular weight when you convert a mass to moles and moles to mass. So, molecular weight of NaOH. So, it is simple to calculate. Actually, it is 40. So, how do we get it? So, sodium it is 23 plus 16 oxygen plus 1 hydrogen, that gives you 40. So, these are the atomic weights. If you know the atomic weights, you can easily calculate the molecular weight. Let us move to the A sub question. So, if you go to textbook and check equation 2.22, we know that LB moles, the definition of LB moles is nothing but mass in LB, that is pounds, divided by molar mass in pounds, molar mass in pounds. So the same thing holds good for gram or kg. Same thing holds good for gram or kg, means gram moles is nothing but mass in grams divided by molar mass in gram. Kg moles is nothing but mass in kg divided by molar mass in kg. So for the sub question A, that is LB moles of NaOH. So mass is given, that is nothing but 20 LB divided by its molar mass is 40 LB per LB mole, 40 LB per LB mole. So this LB cancels, end up in getting, that is nothing but 0.5 LB mole. So means 20 LB is nothing but 0.5 LB moles, 0.5 LB moles. So let us go to the B sub question. So we need to understand the conversion, pounds to gram. So from table A3, that is appendix A. So here we know that 1 LB is nothing but 453.6 gram, 453.6 gram. So therefore first let us convert this, whatever the pounds given, that is 20 pounds were given. So the 20 LB is nothing but we know 1 LB is nothing but 453.6 grams. So if you do the calculation, you end up in getting 9072 grams. So now let us convert these grams to moles. So what is the equation? From equation 2.21, that is gram moles is equal to mass in grams divided by molar mass in grams, So let us substitute this one, that is nothing but 9072 gram divided by 40 gram per gram mole, end up in getting 226.8 gram mole. So 20 pounds, now we converted into grams first, that is become 9072 gram, and then further 9072 gram is equivalent to 226.8 gram mole. So let us move to the subsection C, that is we need to convert it into kg mole, NaOH. It is easy because we have like gram mole, we can easily convert it into kg mole. So from section 2.44, if you check, we know that 1 kg mole is nothing but 1000 gram mole. So that is 226.8 gram mole. So we know that 1 kg mole is nothing but 1000 gram mole. So this become 0.2268 kg mole. So 226.8 gram mole is nothing but 0.2268 kg mole. So this is a simple problem. If you know the simple conversion, you can easily solve this problem. So let us move to the next problem, problem number 2.13. This particular 2.13 is density and specific gravity. Many a times the specific gravities of most of the components are given. So if you know at what conditions the reference points in which it is calculated, then we can easily convert specific gravity into density. In this case, the problem asked is the specific gravity of nitric acid is 1.519 and few things are given, that is 4 degrees centigrade is given, 20 degrees centigrade is given. So first let us understand what is this particular phenomena, and the next question is what is the molar specific volume, and sub question B, the volumetric flow rate of carbon tetrachloride in a pipe is 50 centimeter cube per minute. The density of CCl4, carbon tetrachloride, is 1.6 gram per centimeter cube. So we need to calculate the mass flow rate as well as molar flow rate. So let us solve this problem and understand the solution. Problem 2.13. So let us solve the sub question A. We fetch some data, then we move to solving again sub question 1. Okay, so if you go to this from section 2.4.1, so we know the density of water at 4 degrees centigrade is 1 gram per cc, that is centimeter cube, 1 gram per centimeter cube. So therefore from section 2.42, for a substance with specific gravity 1.5129, that is 4 degrees centigrade and 20 degrees centigrade, okay, the density at 20 degrees centigrade is 1.5129 gram per centimeter cube. So you need to just multiply by the specific gravity is nothing but ratio of that particular density of that component divided by the reference component. Here the water is the reference component. Let us understand what is this particular specific gravity is. So specific gravity. So this is also called as relative density. Means this means, that is what means, that is it is given, right? What is that given? 1.5129, 4 degrees centigrade, 20 degree centigrade. What is the meaning of this? That is this means this specific gravity or relative density is 1.5129 for nitric acid at 20 degree centigrade, reference against water at 4 degree centigrade. Why 4 degree centigrade? The next question is why 4 degree centigrade? It's very obvious. All of us get question, why can't we take it at 20 degree centigrade? Why we need to take at 4 degree centigrade? Because at 4 degrees centigrade, 4 degrees centigrade is exactly 1 gram per centimeter cube. 1 gram per centimeter cube, that is the density of what is 1 gram per centimeter cube. Okay, so that is the reason one can immediately calculate. If the specific gravity is given with respect to 4 degrees centigrade of water, you can just multiply by 1. So whatever specific gravity is given, it is same as that of gram per centimeter cube. We can easily calculate. That is the reason the 4 degree the reference is considered. So let us see the first sub question, that is we know 1 kg is equal to 1000 gram, 1 meter is equal to 100 centimeter. Why do we need this calculation? Because the sub question 1 is what is the density at 20 degrees centigrade in kg per meter cube. Now based on the specific gravity, we understood that the density is 1.5129 gram per centimeter cube. Let us convert this into kg per meter cube. So therefore so density, that is nothing but rho is equal to 1.5129 gram per centimeter cube. So let us convert it. So 1 kg is nothing but 1000 gram and 1 meter cube is nothing but 100 centimeter cube. So if you perform the calculation, you end up getting 1512.9 kg per meter cube. 1512.9 kg per meter cube. So it becomes, this is becomes centimeter cube. Okay, centimeter cancels. Thus this becomes 100 cube. So you can easily cancel the terms, and if you do the multiplication, you are going to get 1512.9 kg per meter cube. So let us move to the sub question 2. What is the sub question 2 is asked? That is what is this molar specific volume? So it is specific volume is nothing but reciprocal of density. But here it is as molar specific volume. Indicates that whatever density is given, first we need to convert it into molar density, then that we can convert it into molar specific volume. So if you know the atomic weights of H, N and O, you can easily calculate molecular weight of HNO3. That is nothing but you can easily calculate H is 1 plus 1 into 14 plus 3 into 16. So it becomes 63. This is the molecular weight of HNO3. So if density of HNO3 at 20 degrees centigrade is 1.5129 gram per centimeter cube, then the gram moles of HNO3 is nothing but 1.5129 gram divided by 63 gram per gram mole, 63 gram per gram mole. So end up in getting, so it is equal to 0.024 gram mole, 0.024 gram mole. So now as I told, the specific gravity. So the first, this is the moles. So the molar density is nothing but, so the molar density is 0.024 gram mole per centimeter cube, So what is the specific volume? Specific volume is nothing but 1 divided by mole, that is density. Here specific molar volume is asked, so it is molar density. It becomes 1 divided by molar density. That is 1 divided by 0.024, it becomes 41.64 centimeter cube per gram mole, So let us move to the sub question B. What the sub question B is asked, the volumetric flow rate of carbon tetrachloride in a pipe of 50 centimeter cube per minute. Volumetric flow rate is given, so and also density is given. We need to convert into mass flow rate as well as molar flow rate. So let us see the sub question 1. So we know that density is nothing but mass per volume, rho is equal to mass by volume. So the mass flow rate, whatever the mass flow rate, mass is equal to volume into density, If it is rate, just we have to mass per time. So mass flow rate is equal to volumetric flow rate multiply by density. So what is the volumetric flow rate given? That is 50 centimeter cube per minute multiply by 1.6. The density is given gram per centimeter cube. Centimeter cube gram cancels, you are going to get 80 gram per minute. So let us see the solution for 2 sub question. So whenever you convert into mass to moles, we need to know the molecular weight. So molecular weight of, that is CCl4 is nothing but 153.8. You can easily calculate. Chlorine is 35.5 and carbon is there. You can easily calculate the molecular weight. So the molar flow rate, you can easily convert this particular whatever mass flow rate is there, you can convert into molar flow rate, that is 80 gram per minute. So we know that 1 gram mole is nothing but 153.8 gram per gram mole. So gram cancels, you are going to get it as 0.52 gram mole per minute. So this is the solution, that is 2.14. It is molecular weight. So it is asked to calculate the average molecular weight of the air. So air is mixture of many components. Many times it is very difficult to calculate the molecular weight of air exactly. So that is the reason we need to go with some assumptions. Let us see the assumption and try to calculate the average molecular weight of air. 2.14, problem 2.14. So if you see the section 2.4.5, the composition of air is approximately, the composition of air is approximately 21% O2 and 79% N2. So why we assume that, sir? Because these are the contained in maximum quantity. That is the reason we assume it is containing 21% O2 and 79% nitrogen. We need to assume it properly. For gases at low pressure, when the gas is at low pressure, so whatever the percentages are there, that could be considered as a mole percent. That is 21 mole percent of O2 and 79 mole percent of N2. So therefore in this case is basis, that is we can consider basis as 1 gram mole of air. 1 gram mole of air. So it contains 1 gram mole of air contains 0.21, because 1 multiplied by 21 divided by 100, 0.21 you can easily calculate. 1 multiplied by 21 divided by 100, 21 divided by 100, it gives you 0.21 gram mole of O2, and nitrogen is 0.79 gram mole of N2, So from the molecular weights, from the atomic weights, you can calculate the molecular weight. Molecular weight of O2 is nothing but 32, and molecular weight of N2 is nothing but 28. So we can easily calculate 1 gram mole of air. 1 gram mole of air is equal to, so it is containing 0.21 of oxygen, that is gram mole of O2 multiplied by its molecular weight, because we need to convert, we need to average the particular molecular weight. So 0.21 multiplied by 32 gram per gram mole and plus 0.79 gram mole into multiplied by 28 gram per gram mole of nitrogen. So if you do the calculation, you end up in getting 28.8 gram. So it is nothing but average molecular weight. You can even also calculate, for example, whenever you have a mixtures, so average molecular weight can be calculated as sigma xi into molecular weight. So summation of this, for example, if it is xi is nothing but mole fraction, that is xO2 into molecular weight of O2 plus x into molecular weight of N2. It's a very simple formula. So if you know mole fraction, here it is 0.21 into 32 plus 0.79 multiplied by 28, you end up getting the same value. It is nothing but average molecular weight. You can usually use this particular formula, and so I is equal to 1 to n. If n number of components are there, you can use n number of components. In this case, it's only 2 components. We end up in getting this particular value as 28.8 gram of, this means 1 gram mole of air is nothing but 28.8 gram. So if you want to write it as molecular weight, it is nothing but 28.8 gram per gram mole. Let us move to the next problem, that is 2.15. Basically we need to calculate the mole fraction. What is the given problem statement? A solution containing 30 weight% water, 25 weight% ethanol, 15 weight% methanol, 12 weight% glycerol, 10 weight% acetic acid and 8 weight% benzaldehyde. What is the mole fraction of each component? So it is, now weight is given. That weight is, we need to convert it into first moles, then we can sum all the moles, then we can go for mole fraction. So let us see the solution step by step. Problem 2.15. So now you can easily calculate the molecular weights. We need to know the molecular weights first. So molecular weights. So that is water is 18, ethanol is 46, methanol is 32, glycerol 92, acetic acid is nothing but 60 and benzaldehyde is 106. So these are the molecular weights. It's very important because weight is given. If you know the molecular weight, you can easily calculate the moles. So total mass could be considered. So if you sum all the mass, you can easily convert it into the mass fraction. You can easily calculate the mass fraction. Here the weight percentage is given. So we know that gram moles is equal to mass divided by molecular weight. Mass divided by molecular. As I told, it is gram per gram mole. So we are going to get it as gram moles. So let us solve in a simple manner. So I will just write down one table. It is easy to understand. We can write it like first column as compound and second column as mass given and third column as molecular weight, that is gram per gram mole, and next one we calculate the gram moles, that is nothing but mass divided by molecular weight, and we can calculate the mole fraction. For each component. We can just make a table like this. It is easy to do the calculation. So what is the compound given? Water is given, and ethanol is given, and methanol is given, glycerol, acetic acid, and last component is benzaldehyde. So if you consider the mass of each component given, if you take the basis as 100 gram, if you take basis as 100 gram, you can easily write down water contains 30, ethanol is 30, this is 30, ethanol is 25, methanol is 15, glycerol is 12, acetic acid is 10, and benzaldehyde is 8. So it should be total 100, and we have know the molecular weight, that is 18, 46, 32, 92, 60, and 106. So let us calculate the moles. Nothing but 30 divided by 18, it is nothing but 1.67. This is 25 divided by 46, that is 0.54. This is 15 divided by 32, it becomes 0.47. And this is 12 divided by 92, becomes 0.13. 10 divided by 60, 0.17. And last one, 8 divided by 106, it's nothing but 0.075. So we need to calculate the total moles. It becomes 3.055. Just sum all these values, you are going to get 3.055. We know the mole fraction, that is mole fraction is what? So individual M is the MA divided by MT. If it is M is the moles, total moles of each component, A component divided by total moles. Here it is 1.67 divided by 3.055. Here this value is 0.55. You can do the same thing for this one, that is 0.54 divided by 3.055 is nothing but 0.18, and then 0.47 divided by 3.055, this becomes 0.15. So same you can do calculation for all these values. This becomes 0.043, and this becomes 0.056, and this one becomes 0.025. Again, if you sum all these things, it should be equal to 1. In the mixture, the summation of the mole fractions of all the component must be equal to 1. Thank you for watching. Please do not forget to subscribe.